Hey everybody, Chris Bryant here. Thanks for dropping by and taking a look at my free CCNA security course here on Udemy. Totally updated for the latest version of the exam, the 210-260 exam, all about virtual private networks. And not only is this course going to come in handy in the real world, it's really going to help you on your CCNA security exam because configuring and troubleshooting VPNs is going to be a huge part of your CCNA security exam. And this totally ad-free course is going to get you ready for success with VPNs on your security exam day and also working with VPNs in real-world networking situations because in the end, that's what it's all about. By the way, this course assumes no prior knowledge or configurations of VPNs. If you've never touched one, you've never seen the terminology, you're actually in the right place because I'm going to take care of that for you. Because for that security exam, the first thing we have to do is get the theory down cold. The labs are great and there's plenty of lab work here, but we've got to tackle a bit of theory first. And we're going to talk about why we would use VPNs in the first place and then compare authentication header and encapsulating security payload. Quite the mouthful, AH and ESP. We're going to talk about the similarities and differences between the two and when to pick one over the other during a live config here in the course. Now, if you don't even know what those are, no worries because I'm going to take care of that for you as well. We're going to go over all of the main steps in VPN creation, in theory, and then during a live lab on live Cisco routers. I'm going to give you a VPN success checklist that guarantees you get every step right every single time because there are quite a few steps here and you got to do them in order and then you got to get them all right. And that's just what we're going to do here. We're going to go over IKE policy creation, application, and of course verifying. Something called a transport set with VPNs. We're going to create those. I'm going to explain them to you clearly and we'll see how to apply them. And another kind of access list, a crypto access list, how to configure it and how to apply it. This gets tricky for a lot of people because they don't know a couple of simple success rules. But at the end of this free course, you will, and you will nail it on exam day. And by the way, even when you're done with that course, this course never stands still because at least once a week, I'm going to add a new security training video from my YouTube channel, including video practice exams, 5-minute video boot camps, and video flashcard exams. All brand new videos created for the latest version of the CCNA security exam. This all starts August 10th. That's when I'll post the first new videos in the VPN course. They'll all be up by Monday, August 15th. So if you join now, you'll be automatically notified when new videos are up. And actually, once you join after that date, you'll still be notified when those new security videos are put up from my YouTube channel. I'm Chris Bryant. Thanks for taking 3 minutes with me here. And I look forward to teaching you all about VPNs. We are about to dive headfirst into the wonderful world of virtual private networking. Before we jump on some labs though, we've got to go through some theory and go see exactly what's going on with some of this new terminology because it's going to be new to you, of course. If you haven't seen VPNs before, it's going to take you a little while to absorb it. There's nothing wrong with that. That's all part of the learning process. But if you are new to VPNs, please spend a little extra time with this video. Watch it a couple of times before you move on to the labs because the labs will be that much more helpful that way. Speaking of theory, the first question I have, maybe the first question you have, is why we VPN in the first place. And the reason is that, the shared channels that we generally use between routers, between WANs or over our WANs, they have a major drawback. They're shared. And if something is shared, what does that mean when it comes to privacy? Privacy may not be the best. It also may not be terribly secure. So I'm sure you already see where this discussion is going. But before we proceed with that, remind me from your CCNA studies, if shared channels aren't exactly private and aren't the most secure things in the world, why do we have them? Cost, because they're cheaper. And we can't have VPNs between every endpoint in the world, but sometimes we've got routers and communications that need to be a little more private than we've got a chance to have over a shared channel. And one of the great things about these virtual private networks is that we bring the privacy to a shared channel because we're actually tunneling through the shared channel. We are digging, if you will, a secure channel or a tunnel through the shared channel. And another great thing about VPNs is that we can apply rules and policies to the virtual tunnel without applying them to the physical channel we're tunneling through. So that is a great feature of VPNs. Three more great features of them is these three features that they bring: data origin authentication, encryption, and data integrity. And I know these are awfully self-explanatory, especially the first one, but I want to draw a clear line between these three. Data origin authentication is done on the recipient end, and it allows the recipient to guarantee the source of the packet. Because we know that all kinds of nasty things can happen along that dotted line, right? That VPN. We could have a man in the middle attack, and they grab some packets and they do some nastiness. So router 3's got to be able to say, okay, did this packet really come from the source IP address that's indicated on the incoming packet? Now, encryption, we know all about that. We know what's going on here. Encryption makes the contents of the packets unreadable during transmission. So even if that man-in-the-middle attack occurs or someone intercepts them in another fashion, then the packets are essentially useless to them. It's like going to the library, stealing a book, and it's written in a language you can't read. Don't steal books from the library. Integrity. Now, integrity, that is also done on the recipient's end, and that is the recipient's ability to ensure that the contents of the incoming packet were not tampered with during transmission. And basically, router 3 here is getting a packet and saying, hey, does this packet say what it said when it left the original sender? So these are three great features to have. Now, that tunnel, it just doesn't build itself. You and I have to do a little building here. And we used to use a little something called the generic routing encapsulation. I love that name. What do you want to call it? I don't know. It's pretty plain. Just call it generic. Well, it was fine for a long time, but there was just one little drawback. GRE is so generic, it does not allow for an encryption scheme. And you read that right, and you heard that right. GRE does not allow encryption, and that's a little too generic for today's world, in my humble opinion, and I'm sure you agree with me. Now, GRE's made a little bit of a comeback. We may talk about elsewhere working with IPSec, but it's definitely not working by itself. And this whopping GRE security hole is corrected by IP security, which is usually shortened to IPSec in VPN discussions and anywhere else. You're almost always going to see it just called IPSec. Now, thankfully, IPSec brings encryption and authentication to the table, and it is a combination of these three things, and I'm not presenting them to you in any particular order, but you should know what these three things are. The first one, authentication header, usually referred to as AH or IP Protocol 51 or just Protocol 51. I think you should know the AH and ESP numbers because I've seen Cisco documentation and some non-Cisco VPN material that make a lot of references just to the numbers. So AH, it defines a method for authenticating and securing data. But I think there's a word missing from there. Now, authentication header, as we'll see, I've got some visuals coming up for you, but AH is literally a header. There's no encapsulating going on, which brings us to, clever segue, the encapsulating security payload, ESP IP Protocol 50. Now, this defines a method for authenticating, securing, and encrypting data. Now, the Internet Key Exchange, the IKE, we're going to be working with a lot of IKE policies live here in the next couple of videos. So this is definitely one we need to know what's going on. And simply, it negotiates the security parameters and the authentication keys that are going to be in use. Let's take a few minutes here to talk about AH and ESP and compare the two. Now, AH brings perfectly good security to the table. There's data origin authentication, there's optional anti-replay protection, and AH does not fully protect the IP header info, but it does protect the payload. And you'll see why it doesn't fully protect the IP header info in an illustration in just a moment. But the thing is with AH, and I repeat it here, it offers data origin authentication. It does offer integrity, but it does not bring data confidentiality, which is a huge difference when you're comparing it to ESP. Basically, AH lets us know the packet's indicated source is indeed the source. It lets us know the packet's contents were not changed during transmission, but it doesn't guarantee that somebody didn't read it along the way. So it does have that lack of data confidentiality. Now, ESP just brings everything we could ever want. Data origin authentication, data confidentiality, anti-replay protection, encrypts the data. It's fantastic. So again, I'm repeating it there, but it does bring us that data confidentiality that we lack when we use authentication header. So the musical question, why would we ever use AH instead of ESP? Why would we do that? This should remind you of a discussion we had during your CCENT studies, your early CCNA work. Two protocols, one of them had a ton of features like windowing and sequence numbers, and the other one didn't have jack. And of course there I'm talking about TCP and UDP respectively. You know, UDP didn't have any of the great features that TCP had, but you know, we use UDP every day for all kinds of things in our networks. And why did we do that? Overhead. And that is one of the reasons that you would choose AH over ESP, is that AH has much less overhead than ESP does. ESP is much more processor intensive than AH. The actual encapsulation and de-encapsulation itself, you know, is a lot of extra work for the router that it doesn't have with AH. There's another reason though. ESP requires what we call strong cryptography. And that is not available everywhere. It's certainly not available on every Cisco device or every non-Cisco device. And it's not even allowed everywhere. It's actually illegal to have certain devices that have strong cryptography in certain parts of the world. And when you start up a device that has strong cryptography, it'll actually have a warning for you beyond the usual copyright notices, that kind of thing. And it'll say, hey, there are places in the world you're not allowed to use this. And if you have any thought that you're in one of those countries or you want to check the list, here's the URL to check the list. So they're very, very careful about telling you that. But that is another reason you might have to use ESP. Now, let's go ahead, take a deep breath, because we're going to hit tunnel and transport mode here for a few minutes. And what you've got to do here is decide between these two modes whether you're running AH or ESP. Now, tunnel mode, that's our default mode. And with this mode, the entire IPSec process is transparent to the end host. Now, the VPN devices, which are the routers in our case, in our labs upcoming, they have a lot to do. Tunnel mode protects the entire packet by doing all of these things. The packet payload is encrypted. If you use ESP, you're going to see a header and a trailer attached to the original IP header and the data. And I have an illustration for you in a moment, I promise. And what we're doing there is encapsulating the original packet. That's where the E comes from in ESP. Now, if you're using AH, a header is inserted, but there's no actual encapsulation. And finally, with this mode, a new IP header is attached, and it's going to reference tunnel endpoint IP addresses. So in a way, you're disguising the original IP addresses that are in the original header by the encapsulation and also just by putting tunnel endpoint addresses on that header. Now, here's a visual that will really help you knock all that theory down. Now, ESP with tunnel mode at the top, you see we've got the header and the trailer there encapsulating the original IP header and the data payload. And you've got that new IP header on the very front. Now, AH with tunnel mode, you see the authentication header, the AH, is inserted right in front of the IP header, and there is a new IP header put on as well with the tunnel endpoint addresses. Now, ESP and AH combination with tunnel mode, you can run ESP and AH. They are not mutually exclusive. And if you do that, you see where everything is. The authentication header is put right in front of the original IP header. Then the AH, the original IP header, and the data payload are encapsulated by ESP. And then you've got that new IP header put on the very front. Whew. A lot going on there. So then finally, after all that's done, the entire IPsec protected packet is sent to the remote VPN device. And of course, that device has to unencrypt and de-encapsulate the packet and then send the original packet to its intended destination. Whew. So you can see there's a lot going on there. So that sounds like a lot of overhead. And transport mode brings us that now familiar, overhead versus protection level argument, because transport mode is going to encrypt only the IP payload. It's going to leave the IP header alone. And it's a bit of an oddity here. You will still have an outside IP header, but it's just going to be a copy of the original header. And that's whether you choose ESP or AH. And this is what we're looking at. You see ESP with transport mode. We've got the header, we got the payload, we got that encapsulated with the header and the trailer. But in the front, we have a copy of the original IP header. And with the authentication header with transport mode, the AH is put right in front of the original IP header, and then a copy of that original IP header is put on the front. So this is not as secure because you're not disguising the original IP header addresses in any way. So somebody can pick those off and start getting a little information just from there. So again, the argument here is overhead. And that's just really, that's what it comes down to. That's what it comes down to really with AH and ESP in many cases. And when it comes to tunnel and transport mode, you've got to make that decision about, overhead versus protection level. I think that is enough theory for right now. Great stuff there, and we're going to start putting some of it into action in the next couple of videos, build some IKE policies, and I'm going to give you that success checklist. I got a 5-part VPN success checklist for you that I want you to memorize, use it on the exam, and then use it in the real world, because I'll tell you, here's a real world note. Here's the thank you for making it to the end of this video. I don't mean it, that was boring, but I know it's 13 minutes of theory. I know that's a lot of theory. So here's your bonus for making it all the way through. I'll tell you the number one thing that causes problems when you're configuring VPNs at the command line the way we're going to do. It's just forgetting a step, because you've got a couple of different policies that have to be negotiated. You got to create something called a transform set. It's not that complicated. Don't let it worry you. Then you've got a crypto access list, which sounds like something you're going to write in another language, but it's the same kind of ACL that you've always written, just applied in a slightly different way. You just got a lot of stuff going on. So I'm going to give you this checklist at the beginning of the next video, or near it anyway, and when we start building it, we'll just check off one thing at a time, because when you have an organized plan to build something like a VPN, you are way ahead of somebody who just says, okay, I'll just sit down with the router and knock it out, because I guarantee you they could spend 15 minutes configuring and an hour and a half troubleshooting. With all that said, thanks for listening, and I will see you on the next video. We are almost there. We're just about to create our first IPSec VPN. There are 5 overall steps to this build, and a quick word to the whys here. If this is your introduction to VPN terminology, or it's been a while and you're a little rusty, don't let it intimidate you. It just takes a little getting used to, because we've got 2 policies to build. We've got a crypto access list to write. We got a couple of other things we got to do. So a lot of little details here, which is why I like to have a checklist in mind when I'm going to write one or troubleshoot one. And the first step of the VPN build is the process initialization. And we don't want just any traffic triggering a VPN build, or we're going to have a lot of VPNs, we're going to have a lot of overhead. So what we're going to do is write a crypto access list to define what we call interesting traffic. That's the traffic that will actually signal to the VPN device, in this case a couple of Cisco routers, that it is indeed time to get to work. I do not choose to configure the crypto ACL first. This is the first step in the build, but I like to get my policies taken care of first. That's the order we're going to take this in. So we're coming back to the crypto ACLs. Be sure you have these 2 phases totally clear in your mind as to what goes where and what's going on with IKE phase 1 and IKE phase 2. They're both negotiations. The first one, this is where the, take a deep breath, Internet Key Exchange Security Association is negotiated. And that's what we call an IKE SA, and that's what we'll be calling it from here on out. When this phase is successful, the result is one bidirectional IKE SA. As opposed to what we get at the end of IKE phase 2, there is a negotiation here, but what we're negotiating here is the IPSec Security Association. So if you say it out loud, it's all the way, it's IP Security Association. Let's just call it IPSec SA. Now when phase 2 is successful, what we end up with is 2 separate unidirectional IPSec SAs. Now of course the big thing to be concerned with here is if phase 1 is not successful, there is no phase 2. So we got to watch our P's and Q's when it comes to that phase 1. Now finally, and just popped up on the screen there, the data transfer is our middle section, and that's where the data is transferred, but you knew that. So we've got the VPN built, we've got our policies negotiated, we have the actual exchange of data, and then we got to tear that VPN down, because once it's no longer in use, we don't want to spend the overhead, we don't want to use the overhead to keep it up. Now, we can configure the tunnel to be torn down at a couple of different times, one of them being when a certain amount of data has gone through. You can also configure it to be torn down after the tunnel has been idle for a given amount of time. We'll see both options here shortly. Now, of course, the first question I had when I read about this the first time was, well, what happens if I'm sending traffic through the tunnel and the tunnel is supposed to be torn down? Yeah, that doesn't sound good. Well, what can happen and what will happen there is that a new SA can and will be negotiated on the fly while the existing SA is still in place. So we're still in good shape if that's what happens. Now we're going to get to the fun stuff. We're going to start configuring. And in this lab, we're going to build a VPN between routers 1 and 3. There's a shared channel between them, frame relay to be exact. And just to show you here, let me go ahead and slide that over a bit. I will send a ping over to 172.12.123.3. Now that's slightly off the screen. I will bring that up. And we're in good shape. So we're using the 172.12.123.0/24 subnet, routers 1 and 3 communicating over frame, no problem at all. And we're going to concentrate our config, or get started actually, on router 1 with these 5 values. And as we go along, we're also going to discuss why you would pick certain ones here of encryption and the hash choices we're given, and also why you might not want to choose others. And also, I will upload a Cisco document. Instead of giving you the link, I'd rather give you the document because the links change. It's some information that's the source for the information you're going to see here, and it's well worth your time perusing it before you take your CCNA security exam. So let's dive right in. With authentication, we're going to do pre-shared keys. With encryption, we're going to do something called 3DES. Every once in a while, you'll see this called TDES for triple DES, but generally it's 3DES. Hash, we're going to use something called SHA, which I like to pronounce SHA. Lifetime, 24 hours. That's the config we're going to put on router 1. That's how long we'd like our phase 1 SA, IKESA to last. And something called the Diffie-Hellman group. We're going to go with group number 5 here. Let's go ahead and bring up the live equipment, because first things first here, we have to make sure that everything is on that should be on. So let's run a little command, our first show command, show crypto ISACMP. And you better get used to this one, because this is the show command, obviously, for our phase 1 info. And what we're going to do is go with policy. And you might say, well, hey, we haven't configured anything yet. Well, we haven't, but there will be a default protection suite here on the router or your VPN device. And there's your default protection suite. We have not configured one yet. And you see a value for each one of the 5 categories I mentioned: encryption, hash, the authentication method, the Diffie-Hellman group, and the lifetime. Notice the lifetime mentions seconds and no volume limit. Remember that. It's good stuff to know. What we want to do, though, is configure a policy that goes along with the values that we had on the board. And let's go back to that. Pre-shared keys, 3DES, SHA for the hash, 24-hour lifetime, and a Diffie-Hellman group of 5. So since that does not match up what we've got here, we've got to create our own policy. That's what we want to do anyway. So the command for that is crypto ISACMP policy. And then we're going to put the priority of the protection suite. I'm going to address what these priorities mean and when they come into play, but note that you have to assign one. There's no option for don't give it a priority. It's got to have one. And we drop into ISACMP policy configuration mode, and now we'll look at our options from there. And you can see it even mentions to us, pardon me, the ISACMP commands. That's nice. So we've got authentication, we've got encryption, group hash, and lifetime. So they're all there, along with the other usual suspects of default, exit, and no. Let's look at our options for authentication first. And we've got a couple of RSA options here. What we're going to do for this lab is you use pre-shared keys. And you'll notice there's no option there. So that's great. We're going to have pre-shared keys. Where are they? Where do we set them? That's coming up. We have to use a separate command for that. Now we're going to choose our encryption. And here we have a 3DES, which is what we said we wanted to use. We have an AES and DES, data encryption standard. Let's go back to the board for a moment, because I want to discuss those 3 with you and what Cisco has to say about them. And also you'll see this information in the PDF that I left for you. DES, you know, it's easy on your router resources, but this is a very big but. It is the least secure of the 3. It was fine in its time, but it is no longer considered secure, and Cisco actually recommends that you actively avoid its use. Now, 3DES or triple DES, it's very similar to DES in operation, but as you'd expect from the name, a block of data is going to be processed 3 times rather than once. And the word generally used to describe 3DES level encryption is adequate. You know, it's okay. It's not great, but it's okay. Now, AES can be really great. The Advanced Encryption Standard, it's much stronger overall security than either one of the other two choices, but also it requires an iOS later than 12.3T to run AES, which in today's network shouldn't be any issue for you, either lab or production. But we're going to stick with 3DES here. Now, I want to bring a couple of terms to your attention that, again, I say this often, you need to have these crystal clear in your head, which is which. Now, all 3 of these are what we call symmetric encryption algorithms because they use a single key that performs both encryption and decryption. That's opposed to asymmetric encryption algorithms, which use 2 keys, a public key and a private key, the public key used for encryption and the private key for decryption. So with all of that in mind, we are going to go with 3DES here. And what else do we have? The hash choices. Officially, the full word is hash. I put has, so that was fine. Now we have that secure hash standard, SHA. And we have our old friend MD5. Remember MD5 from your CCNA studies? It's really one of the first encryption algorithms you run into. And not to badmouth MD5 right in front of it because I know it's sitting right there, but I mentioned this in your CCNA studies, so I'm going to mention it again here, and Cisco does as well in their documentation. You got to watch the use of MD5 because especially the version of it that is used to encrypt passwords in your config, you know, when you run that certain command, remember service password encryption, well, that uses MD5. And what it's really good for is very casual attacks, or I should say defending against very casual attacks. MD5 is easily crackable. That's not just me talking. Cisco will tell you that. Their version of MD5 on the routers, you can pop it. You can find a program to pop it loose in less than 30 seconds, probably less than 5 if you know where to look. And so the problem is with MD5, of course, is not particularly secure, obviously. It's good to prevent what we call the over-the-shoulder network attack. You know, when someone's in your room, your server room that shouldn't be there, and they look over your shoulder and say, oh, his password is CCNA. Well, it's good to prevent that, but that's about all I would really depend on it for. So here, we're going to take SHA. Now, with Diffie-Hellman group, my fault. With the Diffie-Hellman group, you're actually going to use the command group because as you saw, you know, there was no Diffie-Hellman option when we looked at our options a few minutes ago. So here, different devices are going to have different capabilities here. And we would prefer a higher Diffie-Hellman group number than 5, but this is the highest this particular device is going to handle, so we're going to go with that. And the higher the number, the larger the modulus, and it is considered more and more secure. As a matter of fact, I think Cisco tells you really not to use group 1, even though it's still widely available. So let's go ahead and go with group 5 there. And lifetime. Now, I gave you a spoiler on this earlier. On the board, I broke it down into seconds for you. But let's say I came up to you and said, hey, I know you just got your CCNA security certification by taking Chris Bryant's class. I need you to set write the policy, and I need you to set the lifetime of it to 24 hours. That's a great job interview question. Someone comes in, just see if they know what they're talking about. Hey, write me an IKE Phase 1 policy. And if I asked you to write lifetime for 24 hours, what would you put right here? We're going to talk about that and continue this lab at the beginning of the very next video. We're almost exactly where we were at the end of the previous video. Yours truly hit an extra key, so we got a little bit of an extra screen, but we are now at the same place. In that IKE Phase 1 policy, we've set authentication, hash, the encryption, the group number. Now we got to set that lifetime. What's the first thing you ought to do, not just here really, but with any command that has any unit of data that it's going to use, or especially units of time? And that is use iOS help, because some commands are going to use seconds, some time-based commands will use minutes, some will use hours, some will use a combination thereof, and you don't want to enter one number thinking it's seconds when actually it's hours. Now here, if I asked you in a job interview situation or on a practice exam, enter the value that's going to give me a 24-hour lifetime. Well, if I enter 24 here, iOS help wouldn't let me do that anyway. And then you go, and then you run iOS help to see what's going on. The iOS would not allow you to put that value in because the range is 60 to 86,400. But what if I asked you, hey, put in a lifetime of 80 hours? And you put in lifetime 80 thinking that was hours instead of seconds just because you didn't look in iOS help. Just save yourself a lot of trouble and use iOS help to double check, especially your time-based values, but your database values as well. So let's go with the actual default and the maximum, which is 86,400, which is also 24 hours. So we've got our lifetime set up. We need to verify that we wrote our policy correctly. And we're going to use that command we saw earlier when we had only the default, show crypto ISAKENT policy. And now all of a sudden we have two policies, which is a good thing because we just wrote that top one. Protection Suite of Priority 100. Sounds kind of formal. Well, we've got our encryption algorithm, our hash algorithm, authentication method, our Diffie-Hellman group, and our lifetime. You can just check them all right there just to verify that you entered indeed what you thought you entered. Now, I've gone ahead and pre-configured Router 3's policy. I usually don't do that, but you've seen the commands here in this video and the last one. We don't need to walk through that again, but I want to ask you a question actually about that as I remind you about what's going on with the policies or fill you in on it the first time actually. This policy is the heart of IKE Phase 1. Now, when Router 1 initiates the communication, which is what we're going to do eventually, these policies are going to be sent over to R3, the IKE Phase 1 policies, the ISAKENT policies, the ones we just saw. And you can see Router 3 saying to itself, let me see if I have a match for one of those. So what happens then is that Router 3 looks among its own policies for one matching the policy coming in from R1. Now, the lowest numbered policy will be checked first. That's where the numbers come in. If that lowest numbered policy doesn't match, the next lowest numbered policy is checked, and so forth. Now, if a match is found, we proceed to Phase 2. If no match is found, there is no IKE Phase 2. Now, I'm going to show you on the board the config that I put on Router 3, and I gave you a couple of huge hints here. First, I italicized near because it's a near match for policy 100 on Router 1, the one we just wrote. Is near going to be good enough? And I know you could spot it on your own, but I even bolded the one that's different. So authentication, encryption, hash, group, those are all exact matches for policy 100 over on Router 1. What about this lifetime though? I set that to actually half, 43,200 seconds. We get so used to values having to match exactly in networking because frankly in networking values often have to match for anything really to happen. Whether it's OSPF hello and dead timers, some BGP values, all kinds of things, they have to match. PPP, if you configure PPP, you can't have a near password match. That's not going to work out. With OSPF, as I mentioned, if the hello and dead times are different between two potential neighbors, they will stay potential neighbors. They will never form an adjacency. So I'm hammering you over the head with this for a reason, and here's why. With IKE Phase 1 policies, the hash, the encryption, the authentication, the Diffie-Hellman group, that number, they have to match. They have to be an exact match. But lifetime does not have to match. What it has to do, though, is this. The recipient policy lifetime may be equal to or less than the lifetime of the incoming policy. And should the recipient policy lifetime be less than that of the incoming policy, the lower value is used. Boy, that's a good practice exam question. Good job interview question. So you got to know not only that the lifetimes don't have to match, but on the recipient end, it has to be equal to or less than the lifetime of the incoming policy. Then you got to know that the value that will actually be used is the lower value. So there is a lot going on there with our policies. That is going to wrap up our IKE Phase 1 config. So coming up next, we're going to get that IPSec SA configured, set our values for that, and then we'll march on to our crypto ACLs. I'll see you on the next vid. When you're running a longer and more involved config like the one we're writing here with VPNs, it's a good idea to stop after each phase, if you will, and just quickly review your config. Just make sure you're not missing anything, because it's easier to spot something you're missing, say from a policy right here, than when our config is 3 to 4 to 5 times as long, because we got to write 2 policies, a crypto ACO, we got to tie that in, we got to write some pre-shared keys, a couple of other things. So it never hurts to review your config before you're actually finished with the entire thing. So taking a look at router 1's there and router 3's here, just that one little difference in the lifetime, which we know theoretically won't make a difference or won't hurt us. And before we get to the transform sets, though, we do need to create those pre-shared keys. That won't take very long. I apologize, we're a little offline there. There we go. And for our pre-shared keys, what we're going to do is start with crypto IPSec, and we're going to put the key right there in the middle. Set pre-shared key for remote peer. We definitely want an encrypted password, and I'm going to put CCNA for the password here. And we're going to go with the address, and you do actually have to enter the word address, and it's 172.12.123.3. And while we're at it, we're going to go right over to router 3 because I did not pre-config that. Key 6, CCNA address 172.12.123.1. And when you're using pre-shared keys, that's all there is to it. Now let's take a look at these transform sets. First off, talk about what we're transforming here, what we've got, and then we'll configure them. Now, a transform set, it's kind of a merger. What you're doing is defining both encryption and authentication for IKE Phase 2. You're bringing them together because you're defining the encryption and authentication for any IPSec protected traffic using the following: at least one of these 2 security protocols that we talked about earlier, AH or ESP. You can choose to use both. You also have to choose the algorithm to be used by AH and or ESP, depending on the choices you made for the first bullet point. Now on the screen here, in a moment, I'm going to have the choices for the transform set, and the reason I'm showing them to you on the board first is because I want to really point out that some of these are authentication related, some are encryption related, one's compression related. You'll figure that one out, of course, on your own when you see it. But you won't see these comments in paren at the in iOS help. But this is going to be a little smaller font, but here we go. So it's crypto IPSec transform set is the command. Then I'll be asked to name it, and then I used iOS help to see the options. And we see a couple of AH options there. They're both authentication options, one using MD5 and one using SHA. There's our IP compression algorithm option, and quite a few ESPs here, and these are all encryption. You'll see they're using ciphers that we've talked about before with DES, 3DES, and AES. And we've got another authentication here using MD5, and then you have a null encryption option, a seal cipher, and then finally an ESPN, I knew it, ESP transform using HMAC SHA authentication. Now of those, and I know it's an overwhelming list at first, but hang in there. At first, you can only choose one type of each of the following. If you're choosing AH authentication, you can pick one. ESP encryption, one. ESP authentication, one. And then finally, IP compression, the comp LZS option, there's only one there, so that's all you could choose. And let's bring the lab up here. And we've got our keys in. Now we're going to go ahead and start a transform set. And I want to show you some options before I go too far here and show you that the router will actually prevent you from choosing 2 of any of those options that we saw on the board. Let's go with, first off, conft, and then crypto IPSec. Now that's the first thing you got to do. Now we're in IPSec land. We're in phase 2, so we need to use the crypto IPSec command. And transform set is what we're going to do. And you're going to give it a name. And there are some of the options, if not all, and of course different routers, different capabilities will have some different choices, but you see the 2 authentication header choices right at the top, MD5 and SHA. And note, let's say that I chose HMD5. Note for the next option that AH SHA option is gone. So again, you can only choose one. I want to go back to the board and show you that list one more time. You can choose one AH authentication type, one ESP encryption type, one ESP authentication type, and of course IP compression. There's only one there to pick. So we're not going to go with AH here though. We're going to go with ESP, and we're going to use 3 DES for our encryption, and then we'll use SHA for our authentication. So right here, I'm going to go ahead with CCNA, ESP, 3 DES. And notice now that the list of options got way shorter because I can't pick, ESP AES any longer or ESP DES because I've chosen 3 DES. That eliminates the other two choices. So now I'm going to pick SHA. Also notice, one more thing I wanted to point out here, notice the CR there. So that means this is a legal command in and of itself. So the authentication options are still there, but they're not required. You can just go with only encryption. But I'm going to go with ESP, SHA, HMAC. And then you'll notice you're down to your AH options and your IP compression options because you've already chosen your 2 ESP options. That's what I'm going with. And we drop down into transform set config mode. Let's take a look at our options here, and not very many. You've got default, exit, and no. We're used to those, and there's only one other one, and that's encapsulation mode. This is where you choose tunnel mode or transport mode, and you actually have to put the word mode first and then transport or tunnel. I'm going to go with transport here, and that is it for our transform set. It's one long line with crypto IPsec transform set, then your tag, whatever name you want to give it, and then your choices, encryption and or authentication. And now we need to talk about the lifetime here a little bit of IKE Phase 2 SA, the actual IPsec SA. We're going to do that right now. We're going to go right into it because it's a global command. It's not in your transform set. So if you look for it there, by golly, you will not see it. It's crypto IPsec, and what we want is security association. I didn't have to type all that out, but it's a good tip when you're first learning a command to just typing it out all the way instead of shortcutting it a little bit or typing half of it in and let the router take it. I like to type the whole thing out when I'm learning a new command. So we've got show association here. A couple of interesting choices here. We're going to go with lifetime, but I want to discuss that idle time with you because I mentioned in a previous video that you could have this SA deleted after it hasn't been used for a while. And you can do that with idle time. And that should look familiar now, except notice it doesn't tell you how many seconds or what unit of time you're using. So it's a good idea to know that that is seconds. I know you have that down by now, and you certainly even have the range 60 to 86,400 in your head. But if you want to go with idle time, you can do it that way. What we're going to do is take a look at the lifetime options, and notice now that we have the option of seconds, which we would expect by this point, but also kilobytes. So if you want to go by a volume-based key duration and say, okay, the lifetime of the SA is after this many kilobytes goes through, you can do that. And your range gets a little bit larger. So you have to do a little math there to figure out exactly what you want, but that's fine if you want to go with the volume. But if you want to go by time, you'll simply go by lifetime right here. Whoops, I already had that part. Let's try seconds. You actually have to type in the word seconds and then 120 to 86,400. And we'll go ahead and go with 86,400 there. So some extra options there for your Phase 2 SA. But whether you want to use idle time, or you want to tie it down to a certain amount of volume, or you want to tie it down to an overall amount of time, you have all three of those options right there. So I believe, though, we're almost near the end of this config, but we need some kind of traffic to trigger this entire thing. That's our interesting traffic, and we're going to talk about that and define it coming up next. With our IKE policy in place, our IKESA policy in place, both policies written, it's time to put the interesting traffic with a crypto access list. This is how we define the traffic that's going to trigger the build. Because if we don't, the default is we're not going to have a build. You can have all the policies you want, but if you don't have some kind of interesting traffic defined, that is the traffic that puts the entire VPN build into operation, then it doesn't matter how many policies you got. So, what is a crypto ACL? That sounds complicated, doesn't it? I thought it was going to be really complicated the first time I heard of it. Ooh, crypto ACL. Well, it's a crypto ACL is simply an extended ACL. That's all it is. It's going to be applied very differently than anything you've seen before. And by the way, a crypto ACL has to be an extended ACL. It cannot be a standard, as we'll see live here in a few minutes. Thing is that the purpose of the crypto ACL depends on whether the ACL is being applied to outbound or inbound traffic. These are very important roles. For outbound traffic, a crypto ACL permit indicates traffic that will be protected by IPSec. A crypto ACL deny applied to outbound traffic indicates traffic that will not get IPSec protection, but it will still be transmitted. And I say it like that because it's so easy. Your mind's eye sees a deny. It's like, okay, that traffic's not going out. We know better. The traffic's still going out. It's not being denied transmission. It's being denied IPSec protection. That's what we're talking about here with a crypto ACL. What about inbound traffic? Well, one purpose and one purpose only, and that's a permit statement. A crypto ACL permit indicates traffic that is expected to be IPSec protected upon arrival. If it isn't, then that traffic is dropped. So two wildly different operations going on, right, between outbound and inbound traffic. We're way past the days of just doing permit and deny traffic. Some important rules there, but what might surprise you is that since there's such a big difference between outbound traffic and inbound traffic with a crypto ACL, but you will not be indicating in or out when you apply a crypto ACL as you would with a regular ACL, as in this example. I did have this in Cisco router font, but when you enlarge that, it really just burns the retina. So I've got it in regular font here for you. And you can see I'm on fast Ethernet interface. I wanted to apply access list 101. So I put IP access group 101, and we know that is not by itself a legal command. You've got in and out, and you have to specify which one of those it is. But when we apply an ACL, a crypto ACL, you're not going to do that. This is actually what happens. When an extended ACL is used as a crypto ACL, each line is read forward for outbound traffic and backward for inbound traffic. And I've got this on the board for you. We'll write it on the routers as well. But on router 1, access list 103, permit IP host 172.12.123.1, host 172.12.123.3. Source destination, we know that it's an extended ACL. We know the syntax. Now, when this is part of a crypto map, the ACL, again, it's read forward for outbound traffic, and it defines interesting traffic. And that VPN is going to go up when traffic sourced from 172.12.123.1 is leaving the interface for 172.12.123.3. It's going to trigger the VPN build, and that traffic will be IPSec protected. So far, so good. But when traffic comes back, the ACL on router 1 is read backwards, where the source is 123, the destination is 123.1. And when the traffic comes in, router 1 is saying, okay, that traffic better be IPSec protected, or I'm going to drop it like a rock. So while the ACL we write is just like the extended ACL we've written everywhere else, well, the operation of it and the application of it is a lot different. So what I'll do is write this ACL on router 1, the one we just discussed, and a mirror image, not an exact copy on router 3, where the one on router 3 is going to be permit IP host 172.12.123.3, host 172.12.123.1. So both routers will then be able to build a VPN with that interesting traffic. Now, on this subject, it's not on the board, but I want to give you a quick little dad lecture here. If you are cutting and pasting a config this big, I understand. It's a big config. It's a long configuration. And nothing against cut and paste. I do it all the time myself. But you got to be super careful if you're doing that with VPNs, because you can't take the config from one router and just put an exact copy of it on the other and have things work the way you think they're going to work. Because if we did that with the config we have here, if we took all of router 1's config and dropped it on router 3, we'd have to change the ACL line. We'd have to change the ACL 103. We would have to change the setting on the key. Remember the pre-shared key? That had a peer address in it. And we had some other things in there that we would have to change, and you'd have to change this ACL. You got to watch it, because if you are cutting and pasting, you need a mirror image on the other router, not an exact copy. So personally, I think it's easier just to go over to router 3 and config it from scratch. If you really hate to type, I understand that. But my point is, you tend to let yourself in for more troubleshooting than you should have to do if you're copying a VPN config from one router to the other and then just trying to catch all the little edits that you have to make. Okay? One more warning, and this is from Cisco and from me, and it's something that we're going to do here as far as permit host. Using the permit host statement in your crypto ACL, that's perfectly fine, but you should be very wary of using permit any in an ACL that's going to serve as a crypto ACL, especially, of course, if you're doing any for both source and destination, because two things end up happening, and both of them are bad. If you put permit any for your crypto ACL on outbound traffic, what's going to happen? Everything's triggering the VPN and everything's getting IPSec protected. So you got way too much traffic being encrypted and then decrypted to the destination. A lot of overhead. You don't really want to do that. Now, inbound, you got some bad things happening there, because you could have incoming control traffic, protocol keep alives, etc., arriving unencrypted. And you've got an ACL on the router that says, hey, I expect everything that comes in this interface to be encrypted. Well, that's not going to happen. And boy, you're going to have not only malfunctioning network services, but you're going to end up with some lost adjacencies likely as well. So again, using permit host in your crypto ACL is fine. Be very, very wary, careful, don't do it actually, of using permit any for source and destination in that extended ACL. Those are the rules of the crypto ACL, and coming up next, we are going to configure it and put those rules into action. Having covered the crypto map rules in depth and length, we're going to get to our configuration now. The only thing that I've already written is the ACL. I wrote this on R1 and R3, taking care, of course, to put a mirror image on and not an exact copy, and that's the last time I'm going to mention that for at least a few minutes. So let's bring router 1 up, and now we're going to start applying it and making that ACL into a crypto ACL, if you will, and we do that with the crypto map command. And we got to give it a name, so I'm just going to call it CCNA security. And we got to give it something here as far as the sequence number goes. I'm just going to go with 100 here. So this makes it easy to edit a map later if you want to add something, just like ACL sequence numbers do. And now I'm going to go with IPSec ISAKMP. And that's actually going to be it. And we get a note, really a warning. This new crypto map will remain disabled, that means it's disabled now, until a peer and a valid access list have been configured. So you, the experienced network admin, will not panic when you see this. You've probably seen the thing with login and password on a router just when you're setting the console lines or the VTY lines. And I should say, and you've got 5 lines, of course, by default, 0 through 4. And if you put in login first before password, you get this message about, oh, this is invalid until password is entered. You get it 5 times, and the first time you see it, it can panic you a little bit. But after that, you say, okay, just do the password and you'll be fine. Well, as long as you go ahead and set a peer and refer to a valid access list in your crypto map, it's going to be enabled. You're going to be fine. So how do we do that? We're going to do matches and sets here, and we're going to start with match. And you don't see any ACL value here, do you? There's only one match address, and this is actually the one we use. And here it's going to ask for the ACL number. So it's not match ACL or match list, it's match address. And also note that the theory that we cannot use standard ACLs for this operation is verified because you don't even see the standard numbers here. You only see the extended list, the two ranges, and of course we could have named it if we had wanted to. So we're going to go with match address 103, and we're going to do a couple of sets here. Set values for encryption, decryption. And we've got a couple to choose from, I think about 7 or 8, yeah, 8 of them. And we're going to go with peer and transform set. That's what we need, because first off, we got to set that peer because the router told us we had to. That's our allowed encryption / decryption peer, and that is going to be 172.12.123.3. And we're also going to set the transform set, and we are going to just call CCNA because that's the only one we wrote. And if we had written multiple transform sets, you just put them in the order that you want them to try to be used, and just keep putting proposal tag, because that's actually what they are really. Transform sets are just proposals. We'll see that in some debugs when we actually put this baby into operation. So we've got our set peer, we have our set transform set, and we are good to go. Or are we? We're at the step people tend to forget. And it's the last step. So you don't want to leave this out, because if you leave this out, nothing's going to happen. We wrote the crypto map. We wrote the ACL. Then we wrote the crypto map that made that ACL into a crypto ACL, if you will. Now we have to apply it. And you do apply it to the interface in the exact same way, almost, that you would a regular ACL. You're going to use the crypto map command here. And let me use iOS Help here to illustrate to you that the only option here is the name. Always check these when you're troubleshooting, because it's really easy to leave a letter out, something like that. It's got to be exact. And what do we not expect to see here? We do not expect to see in and out, because we are CCNA security certified, and we know the deal with the crypto map and the inbound and outbound rules. So the router's not even going to let us try to apply that inbound or outbound. It is just applied. And that is it. That's the config. You get a little message there, ISOCEMP is on, so you're good to go there. It's a confirmation in this case, actually. You'll always see that after you apply the crypto map to an interface. So we wrote our crypto ACL, we wrote our crypto map, and then we applied the crypto map to the interface, 1, 2, 3. That's it. Now, we're going to go on over to router 3. Let's just go over those commands one more time, because we've got the ACL over here already. Just want you to see them in action again. Then the number, and then you need IPSec ISOCEMP. And that's all we're going to do. We're not going to use those options. We'll save those for another day. We got our little message. So the first thing we're going to do is match on an IP address, because that's the only option we have there. And it's 103 on this side as well. I set the peer to 172.12.123.1. I set the transform set to CCNA. Ah, look at that. Transform set with tag CCNA does not exist. I love this. Now, this is the kind of thing that you're going to see on the live equipment that you will not see, say, on an exam question, that kind of thing. But I did leave the transform set off on purpose, and yes, that is my story, and I am sticking to it. Because I want you to see that when you're writing these, if you refer to a transform set that doesn't exist, it's going to tell you right here and there. Now, if you're showing a config on an exam, I don't think they're going to say, hey, by the way, you got this message on the router that the transform set doesn't exist. But that is something to look for when you're troubleshooting as well. So what I am going to do during the break is write the transform set, and it's going to match the one on router 1 exactly. I'm going to apply it to the interface. Those are the only two, and then I'll just apply this to the interface, and we will be ready to test and verify. We'll verify the config at the beginning of the next video, take a look at it on both sides, make sure everything's there we need, and then we're going to start testing our VPN and debugging it as well. I'll see you there. My friends, the moment of truth has come after all this speechifying and theory that we've learned and the new terminology and a lot of configuration. It's time to generate a little bit of interesting traffic here on router 1 and watch our site-to-site VPN come to life. To do that, let's run a debug, crypto IPSec. And then I'm going to send the interesting traffic over, and hopefully we'll see a couple of screens of info here. And there we go, and things look good. And you might look at that and say, how can you tell that things look good? Well, when you see your IPSec SAs created here at the very end of the communication of the debug, then you know you're in good shape. And a lot of familiar information there. And here for SA trans, I'm going to go back up to the top of this and we'll just take a quick look through. And we send our ping over. You can see the IPSec SA request information is listed right here, and there's a validate proposal request, which we always like. And we go through there. There's a mention of a crypto map right here and a source address and a destination address. That's good stuff to see. Now note, here's the ping result, and the success rate is 80%. Most of the time when you're building a VPN, that first packet is going to time out, and you might even see the second one time out while it's being built. And we'll see that in one of the show commands we'll run in a moment. When I send a ping over now, which I'll do in just a moment, we should see 100% because, of course, the VPN is already in place. And so, again, some familiar looking information there and configurations, but we go through here and the SA is created at the bottom, and we are looking good. Now let's go ahead and send that ping. Actually, let's do the show command first because I want to show you something. No pun intended. Wasn't even a pun. I don't know what you call that, but we'll just move on. You can see with show crypto session, the session status is up and active. Always a good thing. If it were down, we might have an issue. But it's not down. You can see the peer, you can see the port number, you can see the IKE SA information right here. Here's your flow information, and that looks familiar as well. That's our ACL. You've got 2 active SAs, and the origin for the IPSec was a crypto map, so we're looking good there. Let's run show crypto ISAKEMP SA. And here, idle is actually what we want. We're in something called quick mode right now. We didn't get into the different kind of modes we could set as far as an aggressive mode and a quick mode, but I just kept it at the default. So the state of QM idle is actually what we're looking for here. So again, in good shape there. You see the destination and source there at the beginning. And one more I want to run here, and that's our IPSec SA. Lots more information here, but one thing I really want to point out is that you can see the number of packets encapped, encrypted, and then decapped and decrypted. And notice right now everything's at a 4, because when I sent the ping out, we had 1 send error, and there it is. And then the other 4 packets went out successfully, the echoes came back, so that's why we see all 4s there right now. And I will go ahead and send that ping now. I will go ahead and send that ping now. There it is. And let's go ahead and run show crypto IPSec SA. And you can see now those numbers have gone up to 9. So this is a great command. If you think you're having any kind of issue with encapsulation or de-encapsulation, just watch your incrementation right there. And of course, watch your send errors as well. That is it for our site-to-site VPNs. A lot of information here. Like I said, watch the vids as many times as you need to. Pick up that terminology. There's a lot of configuration here step by step, but when you have that little blueprint in mind for the steps, then you're going to be way ahead of the game. And right now, it is time to move on to another section.